So we're now going to start discussing some of the practical considerations in implementing charge pump PLLs. So we know that the charge pump PLL, due to the extra integration, gives us a phase error at time is equal to infinity of 0. And this implies that the input phase is equal to the output phase now, even in the lock condition. Before we didn't see that. But now with the charge pump PLL we do. Now, this can depend on no charge leaking off of the loop filter capacitor when the charge pump is off. And this implies that the capacitor should be lossless or not leaky. Now, real-world capacitors are both lossy and leaky. Leaky just means that charge has some path that it can use to exit the capacitor. So to counter a leaky capacitor, the charge pump has to turn on periodically to replenish any of the lost charge. And what this implies for it to turn on is that we need a finite phase error so that an up pulse is going to be generated. This phase error, due to this resistive loading or leaking from the capacitor, can be found as follows. Here, omega naught is the free running frequency of the VCO. And RC is a model for a resistor in the capacitor model that basically models the charge leakage. So what we want to see with this resistance, and this would effectively be a resistance in parallel with a capacitor, is that if the resistance was infinite, in other words we had an open circuit, then this phi load term goes to 0. Now, we've also made some assumptions about our time domain analysis so far, and that we've been doing our analysis in the continuous time, even though we know that this is a sample data system. So let's mention that sample data systems tend to have more problems with stability, and our continuous time analysis might lead to a false impression that the PLL is stable even when it isn't. Now, the Gardner paper that we've been looking at on charge pumps so far sets a boundary condition for stability, and the boundary condition is that omega n squared is equal to, less than or equal to omega n, the reference frequency, squared, divided by pi times the RC of the loop filter times omega n plus pi. You should note by omega n, in the first case we're talking about the natural frequency, and in the second case we're talking about the input or reference frequency. So what we see here is that the bandwidth of the loop, and the bandwidth of the loop is related to omega n, omega little n. So the bandwidth of the loop is limited by the input frequency omega n, or the reference frequency is really what we should say. A general rule for stability tends to be that we set omega little n to be less than or equal to omega n divided by 10. In other words, we need to make sure that the bandwidth of the loop is less than a tenth of the reference frequency that's input to the PLL. If we fall below that limit, we can continue to use our continuous time analysis rather than having to go to discrete time analysis. Another problem with PLLs is ripple. So in a real charge pump PLL, some current has to be pumped onto the loop even in a lock state. And this current flows through the resistance in the loop filter and generates a voltage pulse every time that the current is pulsed. And the voltage pulse, of course, is just equal to IP, the charge pump current, times the resistance in the loop filter. This is a periodic disturbance that modulates the VCO output and can lead to spurs and noise in the output. And so the solution to this is to modify the loop filter. So we can modify the loop filter by placing an additional capacitor in parallel to the hold capacitor. In parallel to the loop filter capacitor to hold the voltage constant. So our modified loop filter structure then ends up looking like this. Of course, we have our I input coming into this loop filter, and we're measuring the voltage that's developed across the loop filter. That's our control voltage. This adds an additional pole to the response, and our modified frequency response becomes f of s is equal to 1 plus sRC times SC2 divided by 1 plus sRC plus S squared C times C2. Now, if C2 is much, much smaller than C, the loop response isn't affected too much, and the analysis that we did for the prior filter still works fairly well. One thing that should be noted is that having this extra pole in the loop filter reduces the phase margin, and because we now have an additional 90 degrees of phase shift around the loop. The Gardner paper that we referenced elaborates on this if you're interested. We should note, though, that with this filter, the PLL is now technically a type 2 third order PLL. One last thing that we're going to talk about today is the dead zone that can occur when the rising edge of the reference and the output are too close together in time, and the up and down pulses have long turn on and turn off times, and the delay in the reset path is small. So we have a condition here where a lot of things have to happen to make this occur, but it's actually very practical to occur in most PLLs. So let's first assume that the reference and output are not too close together in time. So here I've drawn a reference pulse and the output pulse, and we've exaggerated the scale a little bit, but we have a relatively large delta t. And what happens here is that our up pulse doesn't start until the reference hits. Now the up pulse hits, and then it reaches its logic maximum and saturates. Now, the down pulse doesn't do anything until the output edge starts. Then it goes up. And once it reaches the threshold of the AND gate that's going to turn the reset on in the PFD, then everything will start to reset. So the key here is that the up pulse reached its full output value before it's reset by the AND gate and the PFD. So basically the PFD is working properly here. We got our full amount of charge onto the capacitor that we desired. But let's say that the output and reference are too close in time. So now we have this smaller delta T, and let's look at what happens. So here our up pulse starts to go up, but remember it has a long ramp. The down pulse doesn't start to go up until the output phase hits. It goes up, and then the logic threshold of the AND gate is reached, and then it goes down. But what we should notice is that the output pulse, or that the up pulse also has to go down because the AND gate is going to force the PFD to reset. So here, the charge pump never got fully turned on. Because it never got fully turned on, we don't put the amount of charge that we wanted to put onto the PLL on the PLL. Okay, so we don't fully add the charge that we desire to put on the filter, and this means that the voltage isn't going to be what we want it to be, and so the PLL is not going to respond appropriately. Now this behavior is what we call a dead, it leads to what we call a dead zone. And so what we see is for this is that for small phase offsets, in other words, there are very small differences in time between the reference pulse and the output pulse, the PLL doesn't respond, or at least doesn't respond properly. And so we have this region where of our PFD, so here we're looking at phase error, or V control versus phase error. So we have this region of operation of our PLL where we have a relatively little response if we have a small phase error. And then beyond that range, the PLL responds normally like it's supposed to, so we have a much steeper slope here. So here we see this is where we get the normal phase detector gain from our PFD. This region here where the slope is really small is called the dead zone. Okay, and what we see in this region is that the loop gain drops down to a very small value, potentially even 0, and because the PLL can't respond to phase errors in this range, the phase can kind of just drift freely, and it leads to more noise and jitter in the output. This can be mitigated by forcing the up and down pulses to go high for some period even when the loop is locked. And this is done by adding a delay in the reset path if the AND delay is not long enough. And we'll examine this fix and also start examining some of the different current sources that can be implemented for these charge pump PLLs on Monday in the next class.